So last time we learned, let me see, last time we learned normal distribution, right? Okay, last time we learned normal distribution. So today I will talk about normal distributions, and then the central limit theorem, and perhaps a little bit about the confidence interval if we have time. Oh, by the way, do you have enough time to go over the R console? Do you know how to deal with that? Please go over the software and please tell me if you have any problem with that. Okay. Let's try the following example. Data from the National Oceanic and Atmospheric Administration indicates that the yearly precipitation in LA is a normal random variable with a mean of 12.08 inches and a standard deviation of 3.1 inches. Assume that the precipitation totals for the next 2 years are independent. Find the probability that the total precipitation during the next 2 years will exceed 25 inches, and then find the probability that next year precipitation will exceed that of the following year by more than 3 inches. Yep, I'm going to record the video today. Okay. Then please solve this problem. Do you know how to get the answer? Can you get the answer, everybody? Well, in this case, you should introduce some random variables. Suppose that x1 is the number. No, x1 is the precipitation in the first year. Okay, and x2 is the precipitation in the second year. Okay. Question A, what do you want to do? What do you get? Well, in question A, you want to find the probability that the total precipitation during next 2 years will exceed 25 inches. So you want to find the probability that the sum of x1 and x2 is greater than 25. Make sense? Do you understand? Okay. And then, in order to find this probability, you need to know the distribution of x1 plus x2. Okay. How can you get that? How can you get the distribution of x1 plus x2? First of all, we knew that x1 and x2 follows a normal distribution with a mean. What is that? 12.08, and the standard deviation is 3.1. So the variance is 3.1 squared. Then you come up with x1 plus x2. It should follow the standard normal distribution. It should follow a normal distribution. All right, with the mean and a variance that to be determined later. Then what is the mean value? The mean is the mean of the sum x1 plus x2, and I believe that you already knew how to get the answer, right? It is the mean of the sum, right? And then you get the sum of the two mean values, which is 12.08 plus 12.08. So you get 24.16. That is the mean value of the distribution, the normal distribution. For the variance, you get the variance of the difference, of the sum, and it is the sum of the variance values. So you get 3.1 squared plus 3.1 squared, so you get 19.22. Okay, it means that x1 plus x2 follows a normal distribution with the mean, what is that? 24.16, and the variance is 19.22. So if I standardize the random variable x1 plus x2 by subtracting 24.16 from the sum, and then I divide that the difference by the square root of the variance, which gives you the standard deviation, you come up with the standard normal distribution. All right. Then I denote by z this fraction, so I get a standard normal random variable z. Now we are ready to compute the design probability. This is the probability that x1 plus x2 minus 24.16 over the square root of 19.22 greater than 24 minus 24.16 over the square root of 19.22. All right, and that is the probability that z is greater than. What is the right hand side? Do you know that? What is the right hand side of this fraction, of this inequality? Do you know what it is? I guess the value, let's say 25. I'm sorry, it should be 25, right? So I get 25 minus 24.16 divided by the square root of 19.22. Then I get the number 0.1916. All right. It should be 25 here. Is that all clear, everybody? Okay. Then you come up with the integral from 0.1916 to infinity, 1 over square root of 2 pi, the exponential minus u squared over 2 du. All right. And what do you get? What is the answer for this? What is the answer? What is the answer? You get about 42.4%. All right. Okay. Any questions so far? And remember that you can use the calculators to estimate this integral, and you should use the value 999 for your calculations. All right. Is that all clear, everybody? Is it okay? All right, that is question A. In question B, you want to find the probability that the next year's precipitation will exceed that of the following year by more than 3 inches. How can you get it? For the second problem, you want to find the probability that the next year precipitation will exceed that of the following year by more than 3 inches. That is what you want to deal with, right? So I want to find the probability that x1 minus x1 more than x2 plus 3. That is what you want to do. Or let's say the probability that x1 minus x2 is greater than 3. That is what you want to do. So I have to find the distribution of x1 minus x2. The mean of x1 minus x2 is the mean of x1 minus the mean of x2, and that is 12.08 minus 12.08. So you get 0. For the variance of x1 minus x2, you get the variance of x1 plus the variance of x2. It should be a plus here, okay? And then you get 3.1 squared plus 3.1 squared, and you get 19.22, okay? Therefore, I can say that x1 minus x2 minus 0, and just standardize that, divided by the square root of 19.22. It should follow the standard number distribution. And then I denote this one by z again, and that will give you the probability that x1 minus x2 minus 0 over the square root of 19.22 greater than 3 minus 0 over the square root of 19.22. And then you get the probability that z is more than. What is that number? So you get 0.6843. Okay. And then I want to use the calculators to get the answer 0.6843 to infinity 1 over square root of 2 pi a minus u squared over 2 du. And then what is the answer you can get here? It is about 24.69%. Okay. Is that clear? All right. Okay. Okay, now this is just a summary of what we just learned. Suppose that xi follows a Poisson distribution with the parameter lambda I, and they are all independent. Then we knew that the sum of xi follows a Poisson distribution with the parameter lambda, which is the sum of lambda I. Okay. If xi follows a normal distribution with the mean mi, the variance of I squared. And again, if we assume that they are independent, then we can also prove that the sum of xi is a normal random variable, and you can find the mean, which is the sum of the means, all right? And the variance is the sum of the variance values, all right, sigma I squared. Okay, is that all clear, everybody? That should be okay, right? I hope that you understand that, all right? This is just what we just learned, all right? Now I want to move to the last part of this chapter regarding the central limit theorem, or let's say the normal approximations. Can you hear my voice clearly? Is there any noise? If you have a problem with the sound, please let me know. Okay, everything okay, right? All right. All right. Now on the slide, you can see you can recognize the distributions, the two distributions, right? The first one is a binomial distribution. And the second one is a Poisson distribution. For the second one, I think it is about 20. For the first one, I think it is a binomial distribution. It is 100, 0.4 or something. I don't really remember the number. But it's like you have two different distributions. Okay, so it is very normal if the two distributions are different. However, it's quite strange that when you draw the standard curve like this one, okay, then you come up with two similar things. They're not the same, but they look quite similar. If your concern is the shape of the two of the graphs, right? And see that they have bell shape, pretty much a bell shape. So you see that, well, if n is small, for the binomial distribution, if n is small, or lambda is only 2 or 5 or 0.5, then the distributions are skewed, heavily skewed. But when n is big, okay, for the binomial distribution, or lambda is big for the Poisson distribution, then they become more bell-shaped and symmetric. All right. So it seems that when n is big enough, or let's say the mean values increase, then the distributions become more and more symmetric, and they look more and more normal. Okay, so just like if n is big enough, or let's say the mean values are big enough, then this distribution will reach the family of normal distributions. Okay, that is what we think, and we are going to go over that to see what actually happens when we have just arbitrary distributions, not just binomial distribution or Poisson distribution. Let's go back to our calculation. Suppose that all the xi are independent, such that the mean of xk is m and the variance of xk is sigma squared. It means that they are the same. You know, all these distributions are independent, and they have the same mean values, and they have the same variance values. Okay, and then I denote by Sn the sum of xi, the x bar, the average value of xi. Then we can find the mean of Sn, which is the sum of the means, right? So you get the mean of Sn is simply the sum of the mean of xi, and each term is m, so you get n times m. If you compute the variance of Sn, then you come up with the variance of Sn, which is the sum, so you get the sum of the variance values. How can we do that? The point is that all the xi are dependent. So the variance of each xi is sigma squared. So you can find the variance Sn, which is n times sigma squared. All right. And then we can also find the standard deviation of Sn, which is the square root of the variance. So you get sigma times the square root of n. If you apply these equations, then you can also get the mean, the variance, and the standard deviation of x bar. Okay. You only need to know that x bar is Sn over n. All right. So the mean of x bar is the mean of Sn over n. So you can factor the 1 over n out to get 1 over n times the mean of Sn, which is n. You can also use similar arguments to find the balance of the average value x bar and the standard deviation of x bar. Do you understand? Is it all clear, everybody? Is it clear? Do you get it? Do you get that? Okay. Everything is fine, right? Okay. Then we can we had the following results. Suppose that all the xi are of normal distributions with the same mean, the same variance, and they are all independent. So we have something. So we have more assumptions here. They're not only independent with the same mean, the same variance, they follow the same normal distribution. Okay, then we can conclude that because they are independent, we can say that the sum of the xi follows a normal distribution. All right, with the mean is the sum of the means, right? And the variance is the sum of the variance values. Remember that, okay? And because each IMI is the same, which is m, sigma I is sigma squared. Then we can see that the mean of Sn is n times m. The variance of Xn is sigma squared. All right. So it's sigma squared times n. Then you can find the standard deviation is sigma times the square root of n. All right. So we can get what we can get is that Sn follows the normal distribution with the mean n times m. The variance is sigma squared times n. Okay. And then you can standardize the Sn, which is Sn minus n minus m over the square root of this one, which is sigma times the square root of n. That should follows the standard normal distribution n01. Okay. We can also have a similar result for the average value h bar. So h bar minus the mean value of which is m over the standard deviation sigma over the square root of n. Then you also get the standard normal distribution for this ratio. Okay, understand? Okay, so so after all, we have these two. We have the distribution like this one. All right, do you understand? Okay, so we can do this one for we have the results for the independent normal random variables. Okay. All right, so this is what we have learned so far. We just learned. What is new in this part? Is there anything new? Well, yes, this is, we are now, I think we are ready to mention one of the most important theorem in probability and statistics, the central limit theorem, which says that suppose that all the xi are IID, it means that they are independent, identically distributed. So they are independent and they have the same distribution, okay? Such that they have the same mean value and they have the same variance sigma square, and we still use the notation Sn for the sum, which is an H bar for the average value. And then we can standardize the sum Sn. We can standardize the average value H bar. Okay. Now they don't follow the standard normal distribution. They don't. Okay, because if xi follow, if all the xi follow a normal distribution, then they follow the standard normal distribution. We already proved that. But if they are not normal random variables, then the standard score doesn't follow the standard normal distribution. You don't have it. Okay, basically. However, the point, the most interesting thing is that if n is big enough, if the sample size is big enough, then the standard scores, all these standard scores, follow the standard, approximately follow the standard normal distribution. Do you understand? Is that all clear, everybody? Is that clear? I'm not going to prove it. It takes time to prove it, and we need more knowledge to prove it. So I'm not going to spend time on that. But you should understand the key point, the meaning of the theorem. Do you get it? Do you get that, everybody? Okay, so they don't follow the standard normal distribution, but they approximately follow the standard normal distribution if n is big enough. Okay. Let's consider the following example. A producer of cigarettes claims that the mean nicotine content in its cigarette is 2.4 milligrams, with a standard deviation of 0.2 milligrams. Assuming these figures are correct, approximate the probability that the sample mean of 100 randomly chosen cigarettes is greater than 2.5 milligrams. Can you get the answer? Okay, so in this case, what do you get? Suppose that the let's say x is x1, xi is the nicotine content in the I cigarette. Okay. Then you want to deal with the average value, which is the sum of xi. All right. 100 over 100. If xi follows a normal distribution with a mean 2.4 and the variance 0.2 square. All right. Then you can see that x bar, well, the mean of x bar is this 2.4, and the variance, the standard deviation of x bar is 0.2 over the square root of 100. So you get 0.02. All right. Then I can conclude that x bar minus 2.4 over 0.02 approximately follows the standard normal distribution. Okay. The point is that n is big enough, right? In this case, n is 100. Then if you want, now you want to find the probability that question A, probability that x bar is greater than 2.5, and that is the probability that x bar minus 2.4 over 0.02 more than 2.5 minus 2.4 over 0.02. Okay, and then you get the probability that z, suppose that z is greater than 0.1 over this, so you get 5. Then it gets the integral from 5 to infinity, 1 over square root of 2 pi a minus u squared over 2 du. Do you understand? Is that all clear, everybody? Is that clear? Okay, is that all clear? Now, suppose that I want to apply the theorem in some particular cases. In the first case, I suppose that all the xi follow a Buổi trial. So xi can take value 0, 1, or 0 with probability p or q, okay, which is 1 minus p. And then you can find the mean of xi in this case, which is p, and the variance of xi is p times q. All right. Okay. Then I put x to be x1 plus xn. Then we can see that 3 things. First, x follows a binomial distribution and p, right? Second, the mean of x is the sum of the mean, so you get n times p, and the variance of x is n times p times q. Okay, so we knew that if I standardize the random variable x, I can approximate it by a number, the standard normal distribution, right? So let's say x minus np over the square root of npq approximately follows the standard normal distribution when n is big enough. Do you understand? If x follows a binomial distribution. Okay. Is there any questions so far, everybody? All right. Now, so it means that if you have the probability that x is less than 10, less than or equal to 10, then you can come up with the probability that x minus np over what's that? The square root of npq less than, let's say, I don't have the equal sign here, just less than, all right? And then it gets 10 minus np over the square root of npq. Is there any question so far, everybody? That should be okay, right? Okay. And then we get the probability that z, you can approximate this by z, which follows the standard normal distribution. That number. So let's say I would say c for that. Okay. Where z is the standard normal distribution, c follows the standard normal distribution. Now we may have a problem here. If you have the equal sign here, then it should be the equal sign here. Then it should be the equal sign here, right? All right. You know, this probability is the same as the probability that z is less than c, not equal to. But the first one is not the same as the probability that x is less than 10. Okay, so this approximation doesn't take care of the equal sign. Okay, so how can we deal with that? How can we deal with that? Well, in that case, I need to, if you have the equal sign here, I need to replace 10 by 10.5. So what I'm saying is that the probability that x is less than or equal to 10 is the same as the probability that x is less than 10.5, where x is a binomial random variable. Because x is an integer, then this equation is always true. Okay, and then you can keep using similar arguments to use the standard normal distributions to approximate the probability. Is there any questions so far, everyone? Is that all clear? Then I can come up with the following approximation. I can come up with this. All right. X is less than or equal to k is equals to x is less than k plus 0.5. All right, and you can use the standard normal distributions to get the answer. If x is greater than or equal to k, where k is an integer, then you can use the probability that x is more than k minus 0.5, and you can use the calculation, the standard normal distribution to get the answer. Any questions so far, everybody? Is that clear? Is that clear? Is it okay? Yes? Good. Why 0.5? Well, actually, we don't really know which one is better. You can choose 0.5, 0.4, 0.1. But if you can choose any number between 0 and 1 for that. But because you don't know which one is better, so it is better to select the one at the middle, so that we don't get a bias estimator. Okay, is it clear? Is it okay for you? Okay. All right, let's consider this example. Suppose only 75% of all drivers in a certain state regularly wear a seatbelt. A random sample of 500 drivers is selected. What is the probability that between 360 and 400 inclusive of the drivers in the sample regularly wear a seatbelt? Can you get the answer, everybody? Well, in fact, in this case, just say X is the number. X is the number of drivers who wear seatbelts. Okay. Of course, among 500 drivers. Okay. Then X follows a binomial distribution with the parameter 500 and the rate is 0.75, right? Okay. And then I can get the, I can see that the probability that you want to find the probability that X is greater than 360 and less than what's that, 400. Understand? Okay. And then you get what is this? You come up with the sum probability that X equals K, and then K is 360 to 400. All right, and then you come up with the sum, okay, from 360 to 400, and then 500 to K, and then 0.75 to the K, 0.25 to the 500 minus K. That is what you can do by using the binomial distribution. Besides, we knew that the mean of X is n times P, 500 times 0.75, and that is 375. And you can also find the values of X, which is 500 to times 0.75 times 0.25, and that is 93.75. So I can see that X minus 375 over the square root of 93.75, that should approximately follow the standard normal distribution in 0, 1. Okay. I denote this one by Z, that I get the probability that X is between 360 inclusive, right, less than 400. Then I need to correct I use continuity correction. So I get 359.5 less than X less than 400.5. And then you get the probability that 359.5 minus 375 over the square root of 93.75 less than X minus 375 over the square root of 93.75 less than 400 minus 0.5 minus 375 over the square root of 93.75. And then you get the probability that Z is greater than that number and less than this number. Okay, Then I get the integral. I can approximate it by the integral from this value to that number, right? 1 over the square root of 2 pi times e to the power minus u squared over 2 du. This is the integrand. Okay. Any questions so far, everybody? That's all clear. You can also use similar arguments to get the normal approximation for Poisson distribution, something like this. Okay, you can get something like this. All right, that one. All right, and this is just another example. You can try this example during the break. If you find any problem with that, please tell me. All right. Otherwise, we can move on to the next chapter. Okay. All right. Let's have a break, and then we can continue later. All right. Hello, can we continue? Everybody? Hello? Hello? All right. Can you solve the problem here? Can you solve the problem I gave you? What is the answer? What is the answer? Do you get the answer for this problem? Do you get the answer for this? Any questions so far? Can you get the answer for this question? Still trying? Do you have idea about that? Any idea? Just like, do you have any, you know how to solve the problem somehow? Well, actually, you should say that suppose that x is the number. X is the number of the number of particles in a square meter. Okay. Of dust on that surface. Then X follows a Poisson distribution with the parameter lambda. Here, lambda is the mean of X, and let's say you get 1000. And you want us to find the probability that X is less than or equals to 950. Now you can use Poisson distribution to get the answer, or you can simply use the approximation, the number approximation. So I come up with X less than 950.5, okay? And from here, I can say that X minus the mean of X over the standard deviation of X, which is X minus 1000 over the square root of 1000. That approximately follows the standard normal distribution, okay? Because n in this lambda in this case is 1000, is quite big, right? Then go back to this, you get the probability that X minus 1000 over the square root of 1000 less than 950 on 5 minus 1000 over the square root of 1000. Okay? And then I come up with, let's say this is, I don't know, this one by Z. Then I get the probability that Z is less than this number. What is that number? Let's say 950 0.5 minus 1000 over the square root of 1000. And then you get minus 1.5653. Do you understand? And then you get the integral from minus infinity to minus 1.5653, 1 over square root of 2 pi e minus u squared over 2d, and you can replace this one by minus 999. Is that all clear, everybody? Is that okay? Is that all clear, everybody? Okay. And the answer should be this. This is the approximation you can get. All right. Is that clear, everybody? Okay. And if you use the Poisson distributions to get the answer, then this is what you get. This is the exact answer. Okay, the exact answer is this one. 0.05783629. Okay. Is it all clear? Correct. All right. Is it okay? All right. Is there any questions so far? So we have learned 3 chapters. The first chapter is the chapter about probability, in which you learn the addition rule, you learn the addition rule, you learn the product rule, you learn the conditional probability, you learn the base formula, the total probability formula. And then the second chapter, we learn random variables, including probability mass function and probability density function. And then you learn the cumulative distribution function, all right? And then you learn the relation between those functions. And then we learn some characteristics for random variables. For example, you learn the mean value, okay, the expectation, the median, right? And remember that the mean is used if the distribution is symmetric, it is beautiful. If the distribution has many extreme values, then you may want to think of the median, right? And then you learn the variance and the standard deviation to describe the variation of a distribution. And then you learn the concept of random vectors, in which we talk about probability, the John probability distributions, all right, the marginal distributions, right? And then in the chapter of some special distributions, we learn binary distribution, Poisson distributions, continuous uniform distributions, what else? Exponential distributions and normal distributions. And after all, we learned the central limit theorem, and we use them to estimate, to approximate some the other distributions. Okay, so that's everything we need for the first part of the course, probability. Okay, is there any questions so far? Is that all clear? So if you have no questions, then I will move on to the next one. Okay, all right. Is that all clear? Any questions so far about probability? The last, the first 3 chapters. Not yet. Okay, but then I will move to the next chapter of confidence interval. Okay. So what are we going to study now? Confidence interval. What it is about? You may want you can find the slide from BK Learning. Now I want to tell you the main idea of the confidence interval. Suppose that you measure the current, okay, or the concentrations, and then you can come up with some numbers. Let's say 1, 2, 2, 5, 6. You have 6 values, all right, and then you can come up with the approximation, which is x equals the average value, right? 1 plus 2 plus 2 plus 5 plus 6, all right? Divide by 5, and what is the answer? You get 10, 16, right? 16 divided by 5, and then you get 3.5, 3.2, I'm sorry, 3.2. Okay. And then you may want, if you do another approximation, you can get many numbers, right? You can get 1, and then 10, and then 2, and then let's say, what do you get here? You get, and then 1, for example, okay. And then you compute the average value, which is also 1 plus 2 plus 2 plus 1 plus 10 divided by 5, and then you get 3.2 again, all right? Now, in your opinion, according to you, which one is better? Which one is a better approximation? What do you think? You get 1, 2, 2, 5, 6, and the other one is 1, 2, 2, 1, 10. Which one can give you a better approximation? The first one? Why is that? Why do you think it is the first one? Why do you think that it is the first one? The deviation is smaller. That is a very good comment. I think that is a very good point. We can compute the deviations. Okay, the deviations here, you can find the deviations for the first one. Or let's say the variance first. What is that? We can get, let's say, for the first one, what is that? Actually, 1, 2, 2, 5, 6. And the second one is 1, 2, 2, 1, 10. And the standard deviation of the first, as well as the standard deviation of the second, you get the following result. You get the following result. Okay, you get the first and second lattice one, and it seems that you can see that the standard deviation of the second sample is about 2 times that of the first one. Okay, so we think that the standard deviation of the second one is smaller. Okay, then but right here we just say, okay, the standard deviation is smaller. But why do you think that it is smaller? The smaller the better. Why do you think so? Why do you think that the standard deviation is smaller? The better. Then we may want to find ways. You may want to estimate the error for the approximation. Correct. Suppose that mu is the exact value. Then you want to find mu minus x bar. You want to estimate this one, or let's say x bar minus mu. You want to estimate this one, okay, by epsilon. Understand? And you can determine this epsilon. If the epsilon is small, the approximation is good. If epsilon is big, the approximation is bad. Make sense? Understand? So you want to estimate this the error, the approximation. Okay. So then I may say that x bar like mu is greater than x bar minus mu minus epsilon and less than x bar plus epsilon. Or you can use the notation, a shorter notation, mu equals x bar plus or minus epsilon. Do you understand? Okay, so you can use this notation for that, and this is what you want, what you expect. X bar minus mu, the absolute value is less than epsilon. Do you think so? Is that clear, everybody? No, not the consistent. When some of you mentioned the consistent, well, when you say that the approximation, there are three things that you may want to talk about the approximation. You may want to talk about the consistency. You may want to talk about whether or not it is a bias. All right. And then you want to talk about the effectiveness. All right. Concerning the consistent, you may say that the average value approximation should be closer and closer to the mean value. Okay. And this is always true. If you want to approximate the mean value, you can approximate it by the average value. That is true by the law of large number. Okay, then we have it. All right. Then the approximation is consistent. That is for sure. Okay. Concerning the bias, you want to guarantee that it should be unbiased. Okay. So you want to make sure that the average value of the approximation should be the same as mu. Okay, if you have this one, then x bar is a biased estimator of mu. Okay, and this is another thing that you want to take care of. All right. So the approximation we have is always consistent. The point is that you want to get smaller error for the approximation. Do you understand? Okay. So you want to estimate the value of epsilon. Okay. How can we get it? Can we guarantee that the difference is always less than epsilon? Can we guarantee that or not? Please tell me. What do you think? Can we guarantee that? Can we guarantee that? Everybody? Can we guarantee that? Can we always guarantee that the difference is less than epsilon, a given number? Let's say, can we guarantee that x bar minus mu is less than 0.1? So if we have the approximation 3.2, then we can say that mu minus 3.2 less than 0.1. That's always true. Can we guarantee that? Everybody? Can we guarantee that, everybody? No, indicates that data is skewed. That is right. That is right. The answer is no. Why? Well, suppose that you get 1, 2, 2, 5, 6. Okay, but there's a chance. Not that chance is very small, but there is the chance that it is 600. You get the measurement 600. If it is 600, can we say that H bar minus mu less than 0.1? Can we say that it is true? It is true. It is not true. Okay, it is not true, even though it may occur. Okay, the probability that this case occurs is really extremely small. Okay, it is extremely small, but it may occur. All right. Therefore, we cannot conclude that this is always true. Okay, it means that this could be true with very high chance, but it's not 100%. Okay, we cannot say that it is always true, but we can say that this is a very high. Okay, so instead of determining epsilon such that H bar minus mu absolute value is always less than epsilon, I want to find epsilon such that H bar minus mu less than epsilon with a very high chance. So I want to find the probability that this is true, and I denote that one by gamma. Do you understand what I'm saying? Is it clear? Is it all clear? Okay. This gamma is called the confidence level. Okay. This epsilon is called the error. Do you understand what I'm saying? Okay. And then you come up with H bar minus mu less than epsilon, or you can say H bar mu is greater than H bar minus epsilon, less than H bar plus epsilon, or you can say H bar mu equals H bar plus or minus epsilon. All right, you call any of them a confidence level. I'm sorry, a confidence a confidence interval. Do you understand? Is that clear, everybody? Okay. So we normally fix the value of gamma and determine the value of epsilon. That is what we want to do. Okay. So given gamma, find epsilon. And then you come up with a confidence interval. All right. Is that all clear? So that is what we are going to learn in this chapter. All right. This is what we can do for the mean value and the average value. You can do the same thing for the other parameters. For example, in one, if you are given a distribution, you can have the mean, right, of x. Let's say that is the mu. Then you can find a confidence for that mean value. You have the variance of x. Then you can find a confidence interval for the variance of x. You have the standard deviation of x. Then you can find a confidence interval for the standard deviation of x. You have the median of x, right? Then you can find a confidence interval for the median of x. Is that all clear? All right. So you can always find confidence intervals for those characteristics of the distributions. Okay. Is that clear? All right. But in this chapter, we only try to get confidence intervals for the mean value of some distributions. Okay. Do you understand? Is that all clear, everybody? Is that all clear? So we are given a confidence interval, and we try to find a confidence interval. You are given a confidence level, and you want to find the confidence interval. Okay, the confidence level is usually something like 95%. That is a very, the most popular value you can use in reality. In fact, then or sometimes you can see 99%, 99.5%. Okay. All right, with a very high value, okay, close to 100%. Is it okay? Is that all clear? You see that this is an equation. So if you are given gamma, you can determine epsilon. If you are given epsilon, you can find the gamma. All right. What you want the error to be, to be small, and you want the confidence level to be large enough to be big. Okay. However, we cannot achieve both of them. All right. We normally fix one value and determine the other. All right. So, and we usually fix gamma to make sure that the confidence level is high, and then we determine the error. If you fix the error, let's say you want the error to be small, like 0.01, and and then you find the confidence level, you may come up with something strange, because if you get the confidence level like only 50%, then it doesn't make sense to use that value, right? So we normally fix the confidence level to be high enough, and then you determine the error. Okay. Any questions so far, everybody? Is that all clear? Is that all clear? That should be okay, right? Okay. And you see that the smaller the epsilon, the better the approximation. All right. Okay. All right. here is the outline of what we are going to learn in the chapter. We want, yes, of course, we want to get a confidence level, a confidence interval for the mean value. But can we always do that? There are two cases at least. The first case is for the mean value of a normal distribution. Okay, that is the first case. And then we try to approximate the mean value of some distribution. And sometimes you don't know it. All right. If you don't know it, then you have to use the central limit theorem. We need to use the central limit theorem to approximate the average value, and then you can come up with the distribution of the average value, and then you can get the error. All right, that is the main idea, and we talk about that later. If mu is the mean value of a normal distribution, then there are two cases here. You know the population variance, or you don't know it. All right. If you know the population variance, you can get it. You have some formula for the error. If you don't know it, there is another formula for that. All right. Okay. So let's start with the first case. Suppose that you have many observations. Let's say H1, H2, up to Xn. They are the observations you have. In our group, in our examples at the beginning, we have only 5 observations, right? 1, 2, 1, 2, 2, 5, 10, 5, 6. Then n is 5 in that case. Okay, n is 5 in that case. You have suppose that there are n observations here. And we also suppose that they follow the same distribution, the same normal distribution with the same mean, the same variance. Okay? And sigma and mu is a null. And you want to estimate that. And sigma square is null. For some reason, you do know the value of sigma square, but you don't know the value of mu. Okay, and you want to estimate you want to approximate mu. So for the approximation, that is very easy. The approximation is just we use the average value to approximate the mean value. That's all. So this is very simple. But how can we get the error for that? How can we get the error for that? In order to get the error for that, you need to come back to the definition of the confidence level I mentioned before. It is the probability that H bar minus mu less than epsilon. All right. Now you see that mu is a constant, a null constant, right? Epsilon is another constant. They are deterministic. The average value of X is something that is random, okay, something random. And then in order to get the probability of this inequality of this event, you need to know the distribution of X bar, okay? And do you remember what we learned before? Do you remember that? Do you remember? If all the xi follow the same normal distribution, then the average value follows a normal distribution, okay? And then you can find the mean of H bar, which is the same mu, the standard deviation of H bar, which is sigma over the square root of n. Therefore, I can conclude that the standard score H bar minus mu over the standard deviation square root of n sigma over the square root of n, that should follow the standard normal distribution. Understand? Sometimes we can call the standard deviation of the average value the standard score. I'm sorry, the standard error. The standard error. Okay, SE. So the standard error is simply the standard deviation of the average value. So you have this ratio, the distribution of the ratio, all right? And then you can come up with the probability that x bar minus mu over sigma over the square root of n, it is less than epsilon over sigma over the square root of n, okay? And if I denote by z, this ratio, then this becomes the probability that z, the value of z, is less than epsilon over sigma over the square root of n. Then if I denote by c, the right hand side, then I get c right here. Okay? Do you understand what I'm saying? Is that all clear, everybody? Okay? Is it okay? All right. Okay, now if I draw the graph of the standard normal distribution, then this is minus c. This is c. So this probability is simply that one. Okay, so you come up with this this domain. Clear? Is that clear? Okay. This is gamma. Then I can compute the area of these two tails, and then I come up with let's say I put alpha to be 1 minus gamma, and because the distribution is symmetric, these two tails are the same. So this is alpha over 2, and this is alpha over 2. Is that clear? Then and this is the standard normal distribution. Then if you remember, this value c is simply the upper alpha over 2 critical point. So that is the alpha over 2. The point such that the area to the right is alpha over 2. So I can say that c is simply the alpha over 2. Okay? If you know the value of c, we can say that epsilon over sigma over the square root of n is the alpha over 2. All right? Or let's say epsilon is the alpha over 2 times sigma over the square root of n. This is the formula for the error. And then we can get the confidence interval. Mu equals x bar plus or minus the alpha over 2 times sigma over the square root of n. This is a confidence interval that you can get. Do you understand? Is it okay? Okay, now if you want the errors to be if you want the error to be less than epsilon 0. If you want the error to be less than epsilon 0, then you get C alpha over 2 times sigma over the square root of n to be less than epsilon 0. Or let's say n is greater than C alpha over 2 times sigma over epsilon 0 squared, right? And this is also the formula that you can use to determine the sample size. Okay? Is that clear? All right. Now let's try the following example. In auto racing, a pit stop is where in auto racing, a pit stop is where a racing vehicle stops for new tires, fuel repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these judgments can affect the outcome of a race. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume that the population distribution is normal and the population standard deviation is 0.19 second. Construct a 99% confidence interval for the mean pit stop time. And then how many observations must be collected to ensure that the radius of the 99% confidence interval is at most 0.01. So if you want to solve the problem here, you may want to understand all these numbers. 32, what is that? It must be the value of n, right? Then you get 12.9, that is the sample mean. The sample mean is the average value, okay? And you get the population standard deviation. You need to understand, you need to focus on this one, okay? Notice that this is sample mean, right? This is the population standard deviation, which is 0.19. And that is sigma squared. Sigma. You need to understand, you need to see, you need to be careful with the word population. We had two things. We get the population standard deviation. That is sigma. If you use the word sample standard deviation, that is S. Similarly, if you use the word population mean, That is mu. If you use the word sample mean, that is X bar. Okay? Is it okay? Good. So in this problem, X bar is 12.9, as sigma is 0.19, and is 32. Okay, then you can say mu equals X bar. When I say equals, means it belongs to the interval, not just two values. Okay, X bar plus or minus the error, which is C alpha over 2 times sigma over the square root of n. Then you come up with 12.9 plus or minus a number I will determine later. Sigma is 0.19 over the square root of 32. Now you want to determine the z value. For the z value, you need to have a look at the confidence level. In this case, you get 99%. 99% is the point such that this area is 99%. Or let's say gamma is 99%, and alpha is 1 minus gamma, which is 1%. And this area, the area to the right, is only half of alpha, so you get 0.005. Therefore, the points we have here is z 0.005. Do you understand? Okay. And if you use the table, you could be able to determine the points here. The points such that the area to the right is 0.05, and the area to the left is 0.995. You can determine the points here very easily by using the table or the software. If in the exam, you have to use the table for that, and you should be able to get the point 2.58. Okay, just use the table, you should be able to get that number. 2.58. So this gives you the actual confidence interval. Okay. For question B, you want to determine the number of observations to guarantee that the radius of the confidence interval to be at most 0.01. So the error you want to be is 0.01. So you want question B, you need the error to be less than 0.01 at most, less than or equal to. So n has to be greater than z alpha over 2 times sigma over the epsilon 0 all squared. So I can calculate that. And what's that? N is greater than this becomes 2.58 times sigma is 0.19 over the area 0.01 all squared. Okay. Then after that, you can see that n has to be greater than 2403. Okay. So you can say that n is greater than or equals to 2403. You need to round up the answer. Okay. Is that clear, everybody? Okay. Okay. So I think that's enough for today. Today I just give you ways to find a confidence interval for the mean value of the normal distribution. If you know the variance, if you don't know the variance, you need to use another distribution to get the answer. But that is the story of next time. Okay. Now you can log in the Big Learning for the quiz. There is a quiz. There will be a quiz that you can do, and the deadline for the quiz is it should be until tomorrow night. Okay, so you should be able to have a lot of time. You will have a lot of time to do it. All right. Can you find the quiz now? Can you see it now? Can you find the quiz available? All right. So you have, let me see. I think you have 30 minutes to do it. I think so. Let me check. I gave you 40 minutes, so that's fine. Okay. The deadline is tomorrow night. That is true. Okay. All right. Thank you very much, and wish you have a very happy New Year. All right. Thank you and goodbye.